We're trying to find the sum of the even divisors of this 4-digit even number. So we know by inspection that 2 is definitely a divisor. We don't know how many times 2 divides 5488, so we'll just say 2 to the m here. Okay, now notice that the sum of the digits here is 16, 20, 25. That's not divisible by 3, so 3 does not divide this. 5 also clearly does not divide 5488, so let's try 7. Now a lot of you guys may have seen this cool little trick. If you take the last digit and multiply it by 2, there's a divisibility test for 7. So what I'm going to do is write this down, 5, 4, 8, 8. And again, the trick here, and I did a video on this also, why this works, but what you do is you subtract 2 times the last digits, which is 8 here. So you have 5488, sorry, minus 2 times 8. Y'all, what you do, you have to subtract it from everything else, so let me erase this part right here. Okay, so this is the trick, and again, the proof of it is fairly interesting, but so what you do is you take the last digit here, multiply it by 2, then subtract it from the rest of these, the number formed by the rest of the digits, okay? So this would be equal to 532, okay? But now you could keep this thing up if you want to. You could subtract 2 from this. You would get 49, and that's divisible by 7, right? Or you could also note that this is just equal to 7 times 76, all right? Now what that implies that, and again, it's not clear, but it's just a divisibility test. 7 times 76 is, 532. That intimates that 5 or 7 is also a divisor, okay? So with a little work, we find that 5488 is actually equal to 2 to the 4th. That takes a little bit of time at times 7 cubed. And again, that's not too hard to verify, but we do know that 2 and 7 are the only prime divisors of 5488, okay? Now, we can be systematic right here. We have to exclude m equals 0 for 2, because you see, if m were equal to 0, that would be 1 times odd numbers, right? And we're trying to find the sum of the even divisors, right? And let me be more specific with what I'm saying here. If we allowed 2 to the 0, okay, well, 2 to the 0 is just equal to 1, right? So you would have a 1 inside of here also, not just a 2. You would have a 1 plus 2 plus 4, but the fact that you have a 1 in here would mean that you would have the divisors 1, 7, 49, right? And 343. And you see, we don't want to add up the odd divisors, right? So that's why we have this constraint on the exponents of 2. And if you guys, there's a basic result in number theory here where you let 0 be included. We have to exclude 0, just so we will not get these 1, 2, 3, 4, that's 343, sorry. We would get 4 odd divisors in some, and that would go into the sum. So that's the idea here. Okay, now of course, as far as the 7 goes, the exponent can be unconstrained. Okay, you can have 7 to the 0 if you want. 7 to the 0 would still be 1 multiplied against a bunch of even sum ends, right? Okay, so now another key observation is to note that when you multiply this out, that equals 16 distinct sum ends, right? Because these are all powers of 2 here. These are powers of 7. So you're going to have 16 distinct even divisors because everything inside is getting multiplied by 2 or powers of 2, right? So you're going to have 16 even divisors of 5488 contained in this expansion. We're not going to write them all down, but if you multiply this out, you would have 16 even numbers that are all divisors of 5488, right? And so this is actually fairly easy to add up. This is what they call a finite geometric series. This particular guy here just adds up to, what is this, 6, 14, 30. So we have 30. Now, we could just, if I could add that up in my head, but there's also we could add that up in our head if we felt like it, right? What do we get, folks? We can do that, can't we? It's not too hard, is it? I was going to use the result for a finite geometric series. But anyway, if you go, 1 plus 7 is 8. 8 plus 49 is 57. And 57 plus 343 is 400, right? And again, either one of these, we could have used the finite geometric series result. All right? But no need to do that. I'll show it to you if you want. So the answer to this is 12,000. The even divisors of 5488 sum up to 12,000. Y'all, there is a result here that gives you the same thing. If you're interested, you could write 7 to the 4th. And again, if you think of a finite geometric series, you'll remember why this is true. It's 7 to the 4th minus 1 over 7 minus 1. Okay. So if you carry out this computation, you should get 400 also. But anyway, this is our answer. 12,000. Again, to me, the key to this problem is just to note that you have to restrict, you have to exclude the exponent of 0 on 2. And then you have to just realize that this product yields 16 even divisors, although the 16 is not important. There are 16 even divisors. We answered that question too. But you also know when you multiply this out, these are all going to be divisors of each summand will be a divisor of 5488. That's the key observation right here. So that's it, folks. That's the solution to the problem. That sum is 12,000. Okay, good night.